I mean, I never started like some questions.
Great. So I think there's a whole number of reasons I did the exam wrapper. I think I might explain some of them before. The main reason, I was just actually talking to Sarah about this, is obviously for me it's less about the points for you. I want you to get the points that you deserve and to earn those. But the biggest thing was I don't want you to fall behind. So if there's stuff that you weren't able to show me you're confident in on exam 1, that's going to make you further and further behind if you don't catch up right now. So I'm glad that a lot of you took the opportunity to do that exam wrapper. And even if you didn't turn in the exam wrapper, hopefully you still went back, looked at the exam in a way that you maybe normally wouldn't. So I hope that that was a useful experience for you. It is going to be a lot of time on my part going back through these exams and regrading those questions and looking, did you explain why your answer was wrong, why the right answer was right, all that. So hopefully we don't have to do that on exams 2 and 3, that the scores will be higher and they'll also be closer to the final. So if you don't do it for exams 2 or 3, if we don't do it for exams 2 or 3, you still have the opportunity in the final to show me you know what you're doing. All right. We have a question. We have 33 responses. Is that all the people we have today?
It is.
Hi, Grant. Make sure to staple it, please, and set her up here.
I think 50 is going to be coming in a little bit.
Great. Okay, talk to your neighbor. Do you guys agree on the answer to this question? Justify why. All right, we're up to 41 responses. Yes! And we got 2 more. Come on in. If you haven't turned your exam wrapper in to me already, make sure to turn that in now before class gets started. So staple the parts together. Remember, it wasn't required, so don't stress if you didn't do it, but it's an opportunity. All right. My base is not showing me any of the results. Let's take a look. Woo! A lot of people are saying C. Why? Would anyone like to justify their answer, either if it was C or if it was one of the other ones? And we're going to try to get every single person here to give some feedback today, including Siri. So 1 response per person. How does that sound? All right. Who wants to do this response? Jackson, your 1 response.
Okay, so C is correct because it says measure. And the thing about measuring the strength of all those bonds is that kind of like, you know, how we have resonance structures and how they can flip-flop between different resonances. They can do the exact same thing with the strength of the bonds because if you have double bonds, they are going to be stronger than single ones, but you can't measure that. And since it says measure, it has to be C because you can't measure that.
So I see your point, and I raise you that if you were to go measure, you can actually measure the individual bonds in one molecule. You can look at it by what the distance is between the atoms with X-ray crystallography and a couple of other measurements. And so what we find if we look in nature is that this doesn't actually exist. Lewis structures are great because they give us some idea of what the molecules look like, where the bonded groups are and the lone pairs are in space, but it is not 100% accurate because we can't describe it that accurately. So we have a number of different models. You guys use the PhET simulations. That's another way of representing them, but that has limitations as well. And so this representation is one of 3 that we draw because it's none of the 3. The actual thing that exists in reality that we can measure the length and the strength of the bonds is an average of all 3 of those.
That's what I was saying.
Right. So I wasn't sure if you were saying you can't measure, and so it's a little varied
You
from
can
that.
measure the strength of any given bond, but you can't tell the difference between any one of those 3 because it kind of
Yes,
flip-flops.
great. So we can't tell the difference between any of them. It's not about flip-flopping. It's about it being an average. It's not actually changing between the 3. Just want to make sure on that. And I messed up last class. I realized after class that one of my animations was crap. A resonance arrow is not the one that I drew. This is a resonance arrow. Okay, the other arrow I drew with 2 half arrows, that's actually an equilibrium arrow. When I'm teaching in class, sometimes I don't focus on the details as much, so I got a chance to reflect on that. So whenever we're drawing between resonance structures, we're going to do a double-headed arrow, okay? Sorry about that mistake. All right. Is anyone here interested in a career in medicine? Okay. Do you guys know exactly what career you're going to do? Or you think you want to do? Are you open to other careers in medicine?
No. Yeah.
I would advise you to keep all of your options open. Okay? There's only so many positions in medical school, and that is one of many things you can do to contribute to society through science and medicine. So my wife forwarded this to me. She works at UAMS. So there's a biomedical sciences career fair at UAMS. It's October 18th. They say undergraduates are welcome. They don't have any undergraduates, so it's not UAMS undergraduates. It's you guys. So on Blackboard under discussions, I posted a link. I posted all the information that I was given and a link to all the details. You should register if you're thinking about going. I think it's all day, so figure out what times work for you to be able to go. Okay? Don't want to spend much time on that, but I wanted to give you guys this opportunity that is, I think, pretty awesome. You guys have like a world-class medical facility across the street. So take advantage of that if you're interested in careers in medicine and biomedical sciences. So some of it's basic research, but there's also clinical stuff. All right, so today, hey Marky, do you have an exam wrapper you want to turn in?
Oh, no.
Okay. Yeah, for anyone that arrived late, make sure you turn in your exam wrapper and staple it together if you decided to take that option. So today, we are going to be practicing more of drawing complex Lewis structures, working on naming of polyatomic ions. If you haven't already thought of this or started doing it, that list of polyatomic ions in table 2.5 in your book, one really good way to memorize them is to draw the Lewis structures and go back and forth between the Lewis structure and let me try to name this, let me see what the name is, let me try to draw it. And starting from scratch each time, not looking at the drawing. It's going to be a really good way to practice because there's some kind of tricky Lewis structures in there. So that means we're going to start building off of your modeling lab that you guys have all completed now. So we're talking about looking at what is the actual versus theoretical bond angles that we're going to see between atoms. We're going to talk about molecular shape. We're going to talk about resonance structures. We're going to talk about the difference between bond length and strength in molecules. We just did that a little bit. We're going to be talking about naming and writing formulas for neutral salts. And then bringing this kind of all back to the lab that you guys did. So, what's the molecular shape around the carbon and carbonate? Does everyone know where the carbon is in this molecule? Remember where a line changes directions is a carbon? How many bonds does that carbon have? 4. There's 4 bonds drawn to carbon. 1, 2, 3, 4. How many bonding domains?
3.
Okay. So go ahead and click in your answer to this question. And if you arrived after the start of class, Kiana, did you turn in your exam wrapper if you have it? Great. Can you bring it up to the front, please? And if you didn't get a worksheet, there are worksheets we're putting in the back of class every day so that you grab them on your way in so that we don't have to pass them out and miss people as we're doing it. Can you staple it all together, please? Thanks. All right. How confident do you feel in this? Thumbs up, very confident. Sideways, pseudo-confident. Down, not confident. Okay? One of your best tools for doing this is going to be practice determining what they are and then going and checking the PhET simulation. I think Matt said the other day that when talking to someone who's taking general chemistry before, they suggested that the best way to study is really to make sure that as you go through week by week, you're in complete mastery of the concepts, and then for an exam, you're just reviewing. And I think that it couldn't be said better than that. I think that if you are like, I don't really understand that lab last week, but I'm going to put it off until I study for the exam, you're going to cram, it's not going to work as well, and then you're not going to retain it afterwards. So I highly recommend doing that. So if you identify immediately, I'm not quite sure what the molecular shape is, then I want you to make sure that you identify that and start working on it sooner rather than later. So can I have someone tell me how they determined what the molecular shape is? And we're going to hear from almost every voice in this class today. Okay, Kayla? I was like, Matt? How did you determine what it is?
First, I determined the amount of, I think, ion binding
Okay, so what's the steric number you have?
3.
Steric number around that central carbon is 3. And how many are bonding, how many are non-bonding?
0 are non-bonding, but all are bonding.
So what's the AXE notation? You guys know how to do that now?
AX3.
AX3, E0, we're not going to write E0 because there's no non-bonding pairs. Great. And so based off of that steric number of 3 and a molecular, what's the molecular shape? Or did you do EPG first? Electron pair geometry. So the electron pair geometry is trigonal planar. And then what's the molecular shape? The same. Why? Why are those two the same?
Because you have no lone pairs.
No lone pairs, so we're always going to have the same electron pair geometry and molecular shape when they all, when there's no lone pairs and it's all bonding domains. I agree. Is that what the majority of our class said? Majority of our class did say that. Fantastic. All right, so go ahead and click in what the ideal or theoretical bond angle is where that arrow is pointing. How many degrees is that? Go ahead and click in your response. Couple more seconds. We have a pretty strong consensus about this. I'm hoping we do. We have 2 answers. 109.5, 120, and then someone added 30 right at the end. Which one is it and why? New voice, new hand. Sarah.
Well, I don't know why, but I just know it's 120.
Okay, so it is 120. I want to know why. I want us to be able to describe it. Matthew?
Okay, well, there's 3 bonds. You know it's going to be a planar, and so with 360 degrees for the total circle divided by 3 is 120 for each.
Great, so if we look at where they can be distributed in space, there's 360 degrees around because they're all in a plane. Why are they all in a plane?
Because they're
One response per person today, so hear from new voices. Christina?
Because there's no like repulsion pushing them on the sides, pushing them front or back, so they're just all equally on the plane.
Great, so what Christina's getting at is this idea of VSEPR. VSEPR is about electron domains repel each other. And if they repel each other, they're going to move as far away as they can from each other. So if we have 2 domains, where's the furthest they can get away from each other? Right? This is as far as you can get. If you do this, they're a little bit closer. If you do this, they're a little bit closer if I'm the central atom. If we do 3, it turns out that if my torso is one of them, this is as far away from each other as they can get. If I do this, they're closer together. If I do this, there's now a lower bond angle here and there. So the closest, the most elbow room, the most repulsion that forces them apart you can get is a Y shape. So it looks like this, and there's 120 degrees between each one of those. So the reason I had you guys do the PhET simulation is because I really want you thinking about why do they end up there. It's not about memorizing. If you looked at that lab and then you went home and just memorized the table, that defeated the whole purpose of the lab. So please, if you did that, take that table, go back to the PhET simulations and figure out why those names are what they are, why the domains end up where they do, based on the repulsion properties of those domains. All right, so I agree, 120 degrees is the theoretical bond angle. So then which of these do you think is the best description of the actual bond angle? That sounds like a good idea. So this is greater than 120 degrees on the far left. Exactly 120 or less than 120 is on the far right. What do you think? Is that actual bond angle going to be 120, greater or less than? You can shout with your neighbor if you're not quite sure. All right, make sure your answer is submitted. And hopefully that wasn't coffee.
Sorry, it was water.
That would have been a big waste of coffee. All right, we're all over the place. So, does anyone want to argue their case? Let's hear from some new voices. Trey.
I said that it was going to be greater than 120. The two oxygens down the bottom are negatively charged, and the top is neutral, so they're going to have greater repulsive forces to one another.
I love your logic, but here what plays a bigger role is what's between the atoms, not actually what's on the atoms. But great thinking process of noticing those negative charges.
I said exactly 120 because there's no lone pairs pushing it a different way, so they're going to try to get as far away from each other as they can.
Okay, so what happens when we have lone pairs? What do they do?
They're fat, they're bigger than a regular bond, so they're going to push it, they need more area.
So if this was a lone pair on top instead,
It would be...
the electrons are packed more closely together. They're not spread out between two atoms. And so what Joey's getting at is that the electrons that are in a lone pair need more elbow room or repel a little bit more. Turns out that's actually true for double bonds compared to single bonds as well. Not as much, but it's still true. And so what's the length of a double bond compared to a single bond? It's not the same length. If we talk about a double bond versus a single bond, I'm stepping out of this question for a second.
120 nanometers?
So we just said in the last question 120 versus 140 picometers. So a double bond is shorter, a little more compact. And what about the number of electrons that kind of exist between those atoms?
It's double.
Twice as many. So that means that there's going to be a bit more electron density in a double bond than a single bond. So this is actually, if we have a double bond in a trigonal planar, that bond angle is actually going to be smaller than 120. Not much, but a little bit smaller than 120 degrees. So lone pairs repel more, double and triple bonds repel more than single bonds. So then why is the answer to this question exactly 120? Hello? No, if it was what we just talked about, it would be noticeable. Josh?
The resonance structures of it. So
This isn't what happens. This isn't what exists, right? It's an average of the three resonance structures. So if you went and measured the bond angle, there's no double bond. There's no single bonds. It's an average of one double bond and two single bonds. And so all of them are actually going to have the same repulsion because it's an average of all three of those resonance structures. Okay? That is very different from if I gave you, let's say, this is acetone, nail polish remover. There are no resonance structure. There's a carbon here, carbon here, carbon here. There's more electron density in the double bond than the two single bonds. So that double bond is going to repel those two single bonds down. And that lower bond angle would be slightly less than 120. What does that mean about the two bond angles on either side of the oxygen double bonded to the carbon?
They're larger.
It's going to have to be bigger than 120 because these two bonds are pushed down a little bit, making that angle a little bit wider. Okay, so this is a little bit of a trick question because we're talking about there are resonance structures. If there are no resonance structures, this question would be much simpler. Questions on that? Yeah?
How is that one different than...
Because this isn't actually the structure that we find. Remember, it's a resonance structure, so it's an average of all three of the resonance structures. So there is no double bond here and single bond here. So that principle can't apply because it's an average of them. So that only occurs when you have one bond with a lot more electron density than the other two. All right, so what we just talked about was that electron domains that have more electron density, the electrons are packed closer together, they repel the other domains to a greater extent. So here's an extreme example, tin dichloride. We have a lone pair on top, we have two chlorine atoms. This should be electron pair geometry of trigonal planar. But instead of 120 degrees, that lone pair pushes those two other chlorine atoms way down. What's the molecular shape of tin dichloride, regardless of the change in angle? Talk to your neighbor. What's the molecular shape of tin dichloride based on this drawing? hear a lot of like frogs chirping kind of like Okay, so we know the electron pair geometry is trigonal planar. It's slightly obscured, but that means that the atoms themselves end up in a bent configuration because of the steric number of 3. And like we said, this is also true for double bonds. See how the effect is much less? So we have a double bond carbon to oxygen and then 2 single bonds. That double bond has a little bit more repulsive force, pushes those hydrogens down a little bit, gives them a little bit more elbow room, and then the 2 hydrogens are forced a little bit closer together.
Isn't that molecule formaldehyde?
So what did I say? It is formaldehyde, yes. I don't know if I said the name or not.
No, I was just.
All right, so go ahead, and now we're going to have you draw the Lewis structure for phosphate. I'm going to give you, 1 minute? 1.5 minutes? What question number is this? 5. You might have already done it if you completed the last worksheet, but I want you to draw it again. We're going to work through the appropriate way to have that drawn.
No, I just.
I thought you were saying PO3. No, PO4.
Raise your hand if you need another 45 seconds. We'll do 30.
Thank you.
All together as one?
Yeah, it's mine.
I'm gonna put it all, like staple all, because I don't want to lose one from the other.
It's
Oh, 2 people. I saw somebody else who was gonna come today.
Yeah.
Okay, thanks. All right, let's bring it back together. So once you are working on drawing Lewis structure after Lewis structure after Lewis structure, what you're gonna find is that you can do some shortcuts as opposed to S equals n minus h. We're still going to do S equals n minus h for a couple today to make sure that we know how to use that. But I want you thinking about what trends do we see when we have a bond to oxygen? What are the 2 ways we usually see it? What about nitrogen? What about carbon? What about hydrogen? What about the halogens? All those kinds of things. We're going to start to see trends for how they're drawn out. So to start with, let's do, first thing we need to do before drawing phosphate is, before we count electrons, we know what the formula is. You guys starting to memorize some of these? So phosphate is PO4 3 minus. So that's really important. It tells us what atoms we have, and it tells us what the total number of valence electrons are. We have each phosphorus has 5 valence electrons, each oxygen has 6, and we have 3 more than all the valence electrons of these combined. That's why we have a 3 minus charge. When we finish, we always want to make sure to check all the formal charges on every atom to make sure that they add up to the formal charge on the whole molecule. All right, so if we do S equals N minus H, what is our N for this molecule? Here, 40. And our H, does 32 sound right? Does that include the 3 electrons that are the negative charge? So our shared electrons in this molecule would be 8 electrons, which is how many bonds? All right. One thing I want to keep in mind is, remember, this N is if everything obeys the octet rule. We'll come back to that in a second. All right, so we have 4 bonds. It sounds super easy, right? We do phosphorus, we do 4 bonds, oxygen at the end of each one. And then how many electrons do we have left? We use 8 of the 32 for bonding, so how many more electrons do we have to put around the atom? 24. So 32 is our H, so that means of that, 8 are bonding, and 24 are non-bonding, or lone pairs. So I'm going to go ahead and add those in a different color. We have 4 atoms, so 24, that means 6 each. Or 3 lone pairs each. All right. Now we have all of our electrons accounted for. We have all 32 electrons up there. We have the 4 bonds we're supposed to. We have the 24 valence electrons as lone pairs. What do we need to do next? Let's do the formal charge of each one of the atoms. This is where doing it often and repeating it starts to give you some trends. If we see an oxygen with 1 bond and 3 lone pairs, what's the formal charge? So we do -1, -1, -1, -1. And then phosphorus is supposed to have 5 valence electrons because it's in group 5. We only count 1 from each bond, so it's 4. So is that a plus or minus 1 formal charge? Plus 1. Okay? Do all of our formal charges add up to the 3 minus? 4 negatives, 1 positive. Great. We're not done. Why is this not the best structure we can do? Eric? Were you raising your hand or you changed your mind? Tyler? Okay, we could do brackets over the whole thing to say it's overall 3 minus, yes. But there's something about the structure that is not as good as we can get it. Grant?
You want your phosphorus atom to be neutral?
Okay, so ideally we minimize our formal charges. Every single atom in that has a formal charge. So what's the way we could get rid of that formal charge in the phosphorus?
Double bond.
So we don't have any more electrons, so where do we get the double bond from?
Take the oxygen away from the oxygen.
Let's pick one of the oxygens. Doesn't matter which one. None of them are different, okay? So I'm just going to choose the one on the right side over here, and I'm going to go ahead and add that double bond. Why should that be ringing alarm bells in your head? Why is that immediately you think that might be wrong?
Because it says 4 bonds.
Raising hands, raising hands. Love. Now around this phosphorus, we don't have an octet anymore. We have 2, 4, 6, 8, 10 electrons. Is that okay?
Yes.
Yes, it is. All right, so we kind of mentioned this in class the other day, that anything in periods 1 and 2 on the periodic table, we cannot do this for. It is not allowed. It never happens. We haven't seen it. Okay, when I say that, there's always exceptions, right? There's some crazy group in Switzerland that did a study that found more than 4 bonds of carbon. Okay, stuff happens, it's wonky and crazy. For our class, you're never going to see anything in period 1 or 2 with more than 4 bonds or 8 electrons total. But we're in period 3. Period 3, period 4, 5, 6, any of the other ones now have the opportunity to expand that octet. And so we're going to be talking about that in class on Monday as far as how that happens. But I'll give you a little hint, tie-in. What's the first shell that we have d orbitals in? N equals 3. So that's where that expanded octet is going to be related to once we get into that hybridization. Is that your question, Joey?
No. So, is that what you want us to write? Or because you have the S N minus H and it says 4 bonds.
So why did this I don't want to say fail. Why did that not give us the final answer? What was the limitation of that S equals N minus H? Love? That assumes that everything obeys the octet rule. That's what that N is. So we have to keep that in mind when we're using this equation. It gives us a starting point. That starting point was helpful because it allowed us to show a structure that seemed relatively reasonable, but we could decrease the formal charges. So I do still think that S equals N minus H is the best way to draw a Lewis structure if you haven't seen it before. And then from that, that's our starting point. And then we say, can any of these disobey the octet rule? And if so, we can change around where electrons are placed. So if we were to go back to when Grant suggested that I move the lone pair to the bonding domain for this oxygen, remember we could choose any of those 4 oxygens to do that. That should also be another bell that goes off in our head. What does that tell us? We can have resonance structures. If any of those 4 are equally as good, it means that all 4 of them could have occurred. So how many resonance structures do we have for phosphate? We have 4 places that we can put that double bond. That means the real structure is an average of all 4. All right, questions? So the first structure that we drew was partially correct, but it wasn't as accurate as we can be. I think we've already talked through this. N equals 3 is the first one that can spill over into a d orbital, because remember, valence electrons are s and p, and that's something we'll spend some time with next week. And we've already talked through this. Let's answer this last question here. Bond order. Have you guys seen this yet?
No.
Okay. Bond order, I'll give you a little crash course on this. Not with the eraser. We have a bond order of 1, that's a single bond. It tells us something about the length and the strength of that bond. A bond order of 2 tells us that we have a double bond. It means it's a shorter bond, it's a stronger bond. So what's the bond order of all of the oxygen-phosphorus bonds? Talk to a neighbor, see if you can figure out which one. Is it more like a single bond, one of these ones down here? Is it in the middle between a single and a double bond? Or are they all double bond characteristics? All right, click in your answer if you haven't already. It's frozen, so. We have 44 clicks. All right, can I hear a new voice? Can someone take a guess? This is a totally new concept, so it's fine if you guess and it's wrong. We don't mind that at all. Ashley.
I said 1 1/4 because more of them have only a single bond, but there is that 1/4 chance it'll have a double bond.
I love it. Okay, so you said there's a quarter possibility of it being a double bond, and I would even say that a quarter of the characteristic is double bond because it is an average. It's not either this or that. So let's think about how we can calculate the bond order. The bond order, let's think about the total number of bonds that are in the resonance structures. So how many bonds total do we have? 5 bonds. Over how many domains?
4.
Remember, it's an average of that in each of the different structures. So what does that give us if we simplify that fraction? 1 1/4. So if I told you a bond in a certain molecule had a bond order of 1 1/2, what does that tell you?
There's 2 double bonds.
2 double bonds in what situation?
The bond has to go on, there'd be
if it would mean there's 4 total bonds and 2 of those are double, 2 are single, right? We might not have 4 bonds. That's why I wanted to clarify to make sure.
In that specific one.
Yeah, so if I told you something has 4 bonds and the bond order of all of them is 1.5, that tells you half of them are double, half of them are single. Question mode?
Yeah, how does it take into account resonance structures? It does take into account resonance structures, right? Or bond orders?
Yep. So if there's no resonance structures, a single bond has a bond order of 1. Double bond has a bond order of 2, triple bond has a bond order of 3. And that tells you about the length and the strength of that compared to other ones. If there are resonance structures, then we say, well, what's the average of the total number of bonds that we can place across how many are involved in resonance? And now there are certain examples where you don't have all the atoms around the central atom are in the resonance. So maybe I can show. So if we have a certain structure or something that we drew that has 3 bonding domains around it, are all those 3 bonding domains included in the resonance structure? When I drew this resonance structure, I had to determine where to put all my electrons. I chose that oxygen over this oxygen to put the double bond, and then this one ends up with a negative charge. How many resonance structures does that molecule have? Only 2. So we're talking about this calculation. What's the bond order of either of these 2 bonds? Right? There's 2 domains. This is not involved in the resonance structure. So this is only related to the ones that are included in the resonance structure. Does that answer your question or help out? Maybe
So if they were asking about HC bonds and their bonding domains, or their bond order, you wouldn't take into account the resonance structure because nothing changes.
Correct. So the bond order of this CH bond is?
1.
What about this carbon to other central atom? That one's not involved in any resonance, so that's a bond order of 1. You will see examples where carbon actually is part of a resonance structure, and we'll get into that later in the year. But for now, it's pretty much where we have oxygens around a central atom. How many different places could we have put that double bond versus a negative charge? And that will help us figure out how many resonance structures we have. All right, go ahead and draw the Lewis structure for ammonium. 60 seconds from now. Does everyone know the formula? Can someone say it out loud? NH4 plus. It's an ion. Great. Alright. Getting close. Alright. What's our N for nitrogen? For NH4, sorry, plus. What's our N in S equals N minus H? You said 16? So we have 8 for the central atom, 2 for each of the surrounding nitrogens, 16. Great. What's our H? So we have 16 minus 8, because we have 5 for the nitrogen, 1 for each of the hydrogens. That adds up to 9, but it's a positive charge. So that means that it's 8 for our H. So we should have 8 bonding electrons for S. And then we say, well, how many extra electrons do we have? How many lone pairs do we have? None. Because all of our 8 electrons are bonding, so that means we have no lone pairs. Let's do formal charges. Are there any formal charges in this molecule? Which atom has a formal charge? +1 on that nitrogen. Okay? So this is a habit I want you to get in. Look at the polyatomic ion, draw the Lewis structure, determine formal charges, make sure the formal charge add up to what it is that we expect, which is not a clicker question because we're kind of cruising through this. All right. To make a neutral salt with the ammonium ion, what charge would the salt partner have? Good stuff. A couple more seconds to click in your response. Would it be a positive partner, negative, or does it depend on the situation? Closing out. Why do we have an overwhelming response of people that say it would have to have a negative partner? New voice. Angel?
Is the positive and negative are attracted to each other?
Great. So if we have a positive ammonium, we're going to have a negative partner in order to give a neutral. And the key term here was that when we're talking about the formula of a salt, we're always going to say, what's the appropriate ratio to have a cation, a positive charge, and a negative ion, an anion, in order to get neutral? Have we talked about the term cation yet? I don't know if we did that much. How do we know that cation is positive? Do you guys have any reminders? Any? Cation, there's a plus in the middle of the word. We're not going to get into if you're a cat person or dog person, whether they're positive or negative, all right? But there's a plus, or the T, in cation. That's how I remember the cation is a positive charge. Then anion is the other one. Okay. So then if we had... All right, so fluoride. Fluoride can be a negative ion. So if we had ammonium fluoride, how many fluorides would we need to make a neutral salt with ammonium? A couple more seconds to get your response submitted. Closing out. Overwhelming number of people say 1. Can anyone defend? Why would it be 1 fluoride for every ammonium? New voices. Kiana? Great, so voice is a little quiet. So you want to say it one more time?
Ammonium has a +1 charge, and fluorine has a -1 charge.
Okay, fluoride has a -1. So fluorine is the neutral atom. So fluoride is in group 7. If it were to become an ion, it would gain 1 electron, so it's going to be a -1. So 1-to-1 ratio would be ammonium fluoride, and that would be a neutral salt. NH4, not ClF. And that's actually really nasty stuff. It eats glass and your lungs and a whole bunch of other stuff. So you don't actually want to come in contact with that.
Because it forms HF, which
Is not healthy.
it also takes all the calcium ions out of your blood because it makes you spastic then.
Sulfate. Go ahead and draw sulfate. If you have not already done so. As you're doing it, make sure you go through the same steps. Always think about what the molecular shape electron pair geometry is. Think about formal charges.
Yeah, I was talking about that. I was like, I just don't know.
Couple more seconds for you to work on your own, and then we'll do it together. All right. Bring it back together. What's the formula for sulfate? SO4, 2 minus. I think that's, oops. Let's go ahead and jump right into how many bonds did you draw to the central atom of sulfur? Click in your answer, numerical answer. How many bonds did you draw to sulfur?
It's bonds and not bond domains, right?
Bonds. Yep. A couple more seconds. Closing out. All right, so we have a 2-to-1 mixture of 6 to 4. Why are we not going to do 6 bonds? It exceeds the octet rule, right? We can't do that.
But sulfur isn't in periods 1 and 2, it's in period 3.
So we can expand the octet. Okay, so if we then go and do our S equals N minus H, how many bonds would we have? We would have 4 bonds for S equals N minus H, but we'd have a -1 charge on every atom around the outside, so it's -4, and then we'd have a +2 on sulfur. So what we find is if we pick any 2 of the oxygens, fill in the rest of the structure, we now have a 0 formal charge on the sulfur, and then 2 -1s on each of the 2 oxygens. You guys ready to do bond order of this structure? Yeah. So which of these is the best option for bond order of the sulfur to oxygen bonds in sulfate? Is it not multiple choice? Short answer. You don't want to do short answer? All right, submit your responses super fast. All right. Overwhelming response is Joey's response, 1.5. Why? We have 6 total bonds, 4 domains. So that means an average, if we look at any of those bonds at any point in time, it's going to be halfway between a single and a double bond. Hydrogen sulfate is something that I think is worth discussing really quickly. If we have hydrogen sulfate, does anyone notice a similarity between sulfate and hydrogen sulfate's formula? So we have SO4 2 minus for sulfate. Hydrogen sulfate is HSO4 minus. What's that, Joe?
Take one of the double bonds off the oxygen and add hydrogen.
We could do that, or if you notice the charge changed by 1, so do you think this hydrogen is positive, negative, or neutral when it joined? Positive charge. So we're going to say that for hydrogen sulfate, there's an extra H+. Where's H+ going to be most attracted to in this molecule? One of the negatively charged oxygens, right? So if we then use one of the negative charges that was on the oxygen, that is now this bond here. So we still have 2 double bonds, we still have an oxygen with a negative charge, but now we have an OH bonded as well. Aaron?
Is that because when you add a hydrogen to the sulfate ion to create hydrogen sulfate, you've already got
Yeah, so we'll talk more about equilibrium in second semester and kind of how we get there. I think for now, what I really want you to recognize, I saw some people already working ahead, that hidden within this is actually an SO42 minus. And that's going to be true for nitric acid. HNO3 has a nitrate NO3 minus hidden in it with an H+. So we're going to start to see H pluses kind of covering a lot of different things. One more second. How many total oxygen-sulfur bonds now can be part of the resonance? Can it be all 4? This one can't be part of it anymore. Doesn't have a negative charge, doesn't have a double bond. So we only have these 3 domains. So now what's the bond order? 1 2/3. Okay, so if you look over the rest of the worksheet, at the very bottom, this is kind of what I'm asking you guys to do long term. Look at a giant molecule. This is Abilify, blockbuster drug. You're going to have to go through, do all the things we're doing here, and build on that. We're going to spend more time on Friday. Don't forget the self-care fair is out in the square today. I'll be there with robots if you want to come play. There's tons of other booths.